So with this video, I just want to make a short intro about divergence and curl. Divergence represented by this del operator .a and curl represented by this del operator cross A. Divergence and curl are pieces of the divergence theorem and Stokes theorem. You can see divergence in the divergence theorem, this div piece right here, which is del.a, and you can see curl right here as this del cross A as part of the right-hand side piece. So in this playlist, we do a lot of divergence and Stokes theorem problems, but every time when we do these problems, before we solve on our right-hand side, we need to perform this dot operation and this cross operation, and then simplify before we integrate over the bounds for our volume or integrate over the bounds for our surface, respectively for divergence and Stokes. So for this problem, what we're going to do is, for this video, what we're going to do is look at a couple of different divergence and curl problems, just given a vector, A representing any vector, and then performing the divergence and curl operations in Cartesian, cylindrical, and spherical, and noting the differences. So we're going to scroll down here. So for cylindrical, this is the general solution for the del operator .a for cylindrical, the general solution for the del operator cross A for cylindrical, and then the same for spherical down here, the general solution you can see for spherical, and then the general solution for Cartesian. So one important thing to note about the differences here, Cartesian most people find to be the easiest, but there are kind of general themes that you'll see through all of these. First off, the del operator .a is a product, meaning that the solution may have variables in it, but there is no vector direction. This is just one big magnitude. So no at phi hat or z hat direction in this, and no r hat, theta hat, or phi hat direction in this, or no x hat, y hat, or z hat direction in this. So same for all of these. However, the cross product, the del operator cross A, is a vector. So there will be vector directions, as you can see in the solution components here. So this cross product will give you a vector direction. Okay, so one important thing that I want to note here is these notations here. I know it's a little bit difficult to see. These subscripts here, ax, ay, and az, represent magnitudes for a vector. So for example, if I have 3x x hat plus 2y hat plus 3z hat, my ax, ay, az, those are the magnitudes, which means the piece in front of the unit directional vectors. So 3x, 2, and 3 in this case. So the pieces in front of those directional unit vectors. Same thing goes for Cartesian, or same thing goes for cylindrical and for spherical coordinate systems. So this is just a subscript that means the piece, or the magnitude in the x hat, y hat, or z hat direction. Same thing for these, but the expressions get a little bit more complicated. But if we take a look here, these pieces are the magnitudes in the r hat, theta hat, and phi hat directions. So just the magnitude. If you have a vector, this would just be the number in each of those directions. And then for cylindrical, if we look up here, this is going to be the same. The magnitude in the r, theta, and z directions. And then the same thing over here as it gets a little bit more complicated. So magnitude in the z, phi, r, z, phi, and r. So these are, when we have a vector, these are the pieces that we're going to be subbing out. These magnitude pieces. So we need to find these, okay, plug them into our vector, or sorry, our vector solution for the cross product, or our magnitude solution for the dot products. Go ahead and circle them here. So x, y, and z. And these f or a pieces just sort of represent any vector. It's just kind of a, like you take your actual numerical vector and you're going to plug in the components into this, or respectively any of these. Okay, so hopefully that makes sense so far. If not, we're going to jump into some problems and maybe that'll help clarify for some of you guys. So we're going to start with divergence, and which is just this del operator .a, and we're going to do divergence problems in each of the coordinate systems. So we're going to start with cylindrical here. Okay, or with Cartesian here. So we're going to start with Cartesian. So, okay, first off, we have this vector f. So we're going to plug it into our general equation that we got from up here. So the general equation for Cartesian, and we're going to sub in what we do have. So ax, the magnitude in the x direction, as we can see right there, the magnitude in the y direction and then the magnitude in the z direction. And we're taking the partial derivative with respect to each of these pieces. So let's go ahead and plug that in. Okay, so this is going to be our ax here is 2x with respect to x. Our ay here is going to be xy with respect to y, and then our az here is going to be xz squared with respect to z. Okay, so when we have a partial derivative, we are only taking a derivative with respect to the variable on the bottom. Anything else we're treating as a constant. So first off, what we're going to do is check to see if we have the variable that we care about in the expression. In this case, we do. If we do have the variable that we care about, everything else that we can treat as a constant, we can pull to the outside. Okay, so just with respect to x. Okay, so we do have a y in here. No, we do have the variable that we care about. So let's pull out anything else, treat it as constant. And we do have the variable that we care about, so we can pull out all the other pieces and treat them like they are constants. And then just take the derivative with respect to the variable that we see in the denominator or the bottom here. Okay, so now we have 2 multiplied by the derivative of x with respect to x, which is going to be 1, plus x times the derivative of y with respect to y, or 1, plus x times the derivative of z squared with respect to z, so just the derivative of z, so x times 2z. Okay, that's going to be our answer here. 2 plus x plus 2, or sorry, plus, I'll just keep it kind of in the same order, plus x 2z. Okay, so that's our solution for the first one here. So not too bad, right? Pretty painless. Okay, let's move on down and let's try cylindrical. Things will get a little bit more complex as we keep going here. So for the cylindrical coordinate system, notice that we have these multipliers here that are going to make our problem a little bit more complicated. So we need to be careful that we include those. And these pieces that you see in the parentheses here, we're going to take the partial with respect to this first before we do this part. Okay? So hopefully this will make sense here, but we're kind of going to go through this step by step. Okay, so we have the e. E is our vector. So we're going to plug it into our a, quote unquote, any vector. So we're looking for, in cylindrical, instead of x, y, and z, we have r, phi, and z. Okay, so we have r hat here, which means that this magnitude right here is our AR, or the magnitude in the r direction. A just representing any vector here. From our expression, we have this a. Okay, so we're going to go ahead and plug in this for AR here. Note that we don't have an a phi, that's equal to 0, and we don't have an az, that's equal to 0. So we're going to drop out these pieces, and we're just going to solve this piece right here. Okay, so we're going to end up with, for r, then we have the partial with respect to r of r multiplied by our expression here, r cosine of phi, okay, because that's our AR, our magnitude. Okay, so like I said before, the pieces that you have in the parentheses, you have to do the partial derivative with respect to that first. So the partial derivative with respect to r of r squared cosine of phi. Okay, so we have the variable in the denominator, we do have it, so everything else we can treat like a constant and we can pull it to the outside. And we're not going to forget our 1 over r piece here, that's also very important. Okay, so let's pull out what we can treat as a constant. Okay, so we can pull out this cosine of phi, so 1 over r times cosine of phi times the derivative with respect to r of r squared. Okay, so we're going to end up as 1 over r times cosine of phi, and then the derivative with respect to r is just going to be 2r. So we're going to end up with 2 cosine of phi for our answer here. Okay, not too bad, right? So we just really need to pay attention to these pieces here and make sure that when we do the partial that we leave our r on the inside first, okay? All right, so now moving on to spherical. Let's try a spherical problem. So again, I have a general expression right here that I just copied from that cheat sheet above that I showed you guys in the beginning of this video. And what we're going to do is see what we have here. Okay, so spherical, we have r, theta, and phi are our components, and because we have a phi hat, we know that we have an a phi, so that's a magnitude, that's a little thick, a magnitude in the phi hat direction. That's going to be equal to this piece that's before the phi hat unit vector. So the piece before the phi hat unit vector is equal to a phi. Okay, let's look at our expression here and see where a phi is and where our magnitudes are. So we have magnitude in the r direction, magnitude, oh, I'm sorry, a phi, I keep a theta, theta, phi. Okay, so let's see here. So we have this magnitude here for this piece. This is going to be equal to 0 because we don't have anything in this direction, in this phi direction. This r, we don't have anything in front of an r hat unit vector, so this piece is going to be equal to 0. So we can cancel this piece, and we can cancel this piece, okay? So we're just going to end up with this middle piece right here, and this is where we're going to plug in our a theta value. Okay, so let's go ahead and do that. Okay, oh, I'm sorry, dot. We're still doing del operator dot a. So the divergence, not the divergence theorem, just the divergence. R sine of theta, or d theta, and then let's plug in our a theta here. And notice that we have a multiplier for sine of theta. You can scroll up to the cheat sheet and see that that's in there. Make sure that you keep those in the parentheses and that you do the partial derivative with respect to that first. Okay, so we have r e to the 2, maybe I'll write this differently so you can tell that we're plugging it in, e to the 2 phi, which is our a theta piece, right, because it's at the magnitude in the theta direction, and that's going to be multiplied by sine of theta. Okay, so, all right, so what can we take out here, right? So we're taking a derivative with respect to theta. We have a theta piece, so we can treat everything else like a constant, and we can pull it to the outside when we have a theta piece. If we don't have a theta piece at all, the whole thing is a constant, and the derivative is 0. We'll hopefully see that a little bit later down. Our sine of theta. Okay, and then we're pulling out this r e, the 2 phi, right? And then we're just taking the derivative with respect to theta. Sorry if I said phi in the beginning. I don't mean to be inconsistent here. Okay, the derivative with respect to theta of sine of theta is going to be cosine of theta. Okay, and note we do have an r here on the denominator, so we can cancel these guys out. So we can cancel out an r here, and we can cancel out an r here, because right, it's going to be r multiplied by 1 over r sine theta. Okay, so then we're going to move those pieces to the next step. We're going to end up with e to the 2 phi multiplied by cosine of theta multiplied by 1 over sine of theta. Right? Yeah. Okay, because that sine theta is on the outside. All right, so 1 over sine theta, and we're only taking the partial with respect to what's in the parentheses, which is why that's broken up there. Okay, so let's do, so cosine theta over sine of theta, and then we have e to the 2 phi. And let's double check and make sure that answer is correct, and it is. Okay, so this is our final answer here. Okay, so we just did divergence in Cartesian, cylindrical, and spherical. Okay, all right, so next what we're going to do is we're going to do curl. So we're going to start with curl for Cartesian. Okay. And we're using our general expression here for curl for Cartesian, and our general vector here, this f is just any vector for this expression. It works out that our vector name is also f, but this is just a general equation. Okay, so let's see what we have here. So we only have a z component that we see here. So just a z component, which means that we have these pieces we're going to cancel, because we don't have the we don't have a magnitude in front of an x hat or a magnitude in front of a y hat, so we don't have these guys. So they're going to go to 0. Okay, so let's plug in and solve for the pieces that we do have. Okay, so we're going to simplify this expression a little bit. Okay, so what do we have for f of z? Well, we have e to the negative x, so let's go ahead and plug that in. Okay, it's going to be equal to, what is our z piece? Our z piece is e to the negative x. Maybe I'll put it in a different color so it's a little easier the negative x. So we're plugging in. And this is in the x hat direction because, again, the cross product does have a vector direction. And I'm going to go ahead and add, let's do a subtract here. Just distributing the negative. Okay, and then e to the negative x. And that's with respect to x. Okay, so let's look at something really important here. Okay, so we're going to start with this first piece, partial with respect to y. So let's notice that we don't have any y terms here, right? There are no y terms, there's nothing to pull, there's like no base terms. So if we don't have any y terms, we can't pull anything to the outside. This whole piece is a constant, right? And we're basically taking the derivative of a constant, so the whole expression goes to 0. It would be the same as doing like the derivative of just a number is equal to 0. So derivative of a constant. If we don't have any y pieces, or if we don't have any pieces that match our denominator, then it just goes to 0. Okay, now this piece, we do have x pieces here. So we're going to continue over here. So the partial, so the derivative of e to the x is just negative e to the x. So we'll have a negative e to the negative x in the y hat direction. So e to the negative x in the y hat direction is our solution here. Okay, so again, because it's a cross product, we do have a vector direction in our final answer, so that's good. Okay, so now moving on to our cylindrical coordinate system. Okay, so let's look at our starting vector. So our starting vector here, we have a z hat piece, so the piece in front of z hat is going to be az, but we don't have an r hat component or a phi hat component, okay? So there's no r and there's no phi. So no phi, no r. So again, no phi and no r. These are equal to 0 because we don't have them in our vector, okay? They're equal to 0. Okay, so, but we do have an az piece. So, okay, so this whole piece cancels, yeah? Well, I guess that's obvious already. I won't have to, because it's a little overkill. Okay, so let's see what we do have left, okay? So we're going to end up with 1 over r, partial with respect to z of phi r hat plus negative partial of az with respect to r in the phi hat direction. Yep, that looks good. Okay, so let's plug in our az and simplify. Okay, and then we're going to end up with 1 over r. And notice that when we do this partial here, okay, r cosine of phi, so we're taking this interior partial derivative first, okay? R cosine of phi with respect to phi here. Oh, and note that this phi and this phi are the same. It's just like a drawing style, like it's just a style in terms of drawing that angle. So if you do see those, just know that they are exactly the same. Cosine of phi with respect to r in the phi hat direction. Okay, so what are our denominators here? Well, we have d phi, and then we have a phi piece, and then we have dr, and we have an r piece. Okay, so anything that's not a piece related to the denominator, we can treat it as constant and kind of pull it out of the expression. I think it makes it a little bit easier to see what's going on. But let's go ahead and do that. So we have 1 over r, and then we're going to pull this to the outs. Oh, sorry. We're going to pull the piece that's not related to piece to the outside. So we're going to have over here, we're going to have cosine of phi, right, times derivative with respect to phi of, oh sorry, I pulled up the wrong piece. So we're going to have r, and then derivative with respect to cosine of phi, d phi. Okay. Because r is a constant for this first piece here, r hat. Okay. If this was the dr for the denominator, we wouldn't really be able to pull out that r again because we care. You'll see it on this side actually. I won't try to explain here. Okay. So we're pulling out this cosine of phi, and then we have derivative with respect to r, dr, right? In the phi hat direction. Okay. Now what are our derivatives? Well, the derivative of cosine of phi is negative sine of phi, and the derivative of r is just 1 with respect to r. So let's go ahead and plug those in up here. So we have 1 over r times r. It's going to be 1 times negative sine of phi, and that's going to be in the r hat direction. So right here, so negative sine of phi in the r hat. We just did the derivative there. Okay, and then we have minus, right? Minus cosine of phi, and then the derivative of r with respect to r was 1. So multiply by 1, and that is in the phi hat direction, so phi hat. Okay, so our answer is negative sine phi r hat minus cosine, minus cosine of phi in the phi hat direction. And notice that we can have, oh, I'm drawing my phis differently. That's going to be very confusing, huh? I'll make those, they should look the same here because they are the same. Okay, let's double check here and make sure that that's right. Cosine of phi, yes. And notice that we can have, like, this phi is in the r hat direction, this phi is in the phi hat direction. These variables, it doesn't matter if they don't line up. Like, I could have r in the phi hat direction. Some people are tripped up by that. It really, those two things, the variables don't have to line up with the directional unit vectors, so don't, if you have that in your head, you know, get that idea out of your head, or else you're going to trip yourself up pretty bad. Okay, so, all right, so our last piece here. So we have an r hat direction. So for spherical, we have r hat, theta hat, and phi hat. Those are the directions for spherical, just like x, y, and z for Cartesian. This is what they are for spherical. So this is our AR, right? But we don't have an A phi, or A theta, and we don't have an A phi. Sorry, I keep mixing up the names for phi and theta, I apologize. So we don't have an A phi, and we don't have an A theta. And this phi, again, is equal to the same. These are the same. This is probably just a lazier way of writing phi. Okay, so, all right, let's cancel what we don't have here. So we don't have an A phi piece. Don't have an A phi piece. It's going to be 0. So we don't have an A phi piece, and we don't have an A theta piece. This is theta, this one is phi. Okay, now here we do have an AR piece, so we're going to keep that guy, but we don't have an A phi piece, so this is going to go to 0. A theta, we don't have that, so that's going to go to 0. Okay, so the pieces that we are keeping, we have AR here, and we have AR here. Looking through the rest of this expression, we don't have it anywhere else, so let's go ahead and simplify and see what we have left. Cross A is equal to, so this whole term, this whole first term cancels. We don't have anything in the r hat direction in the end, but we do have r over sine of theta, it's a partial of AR over phi in the theta hat direction, plus 1 over r times negative partial with respect to A, or partial with respect to theta AR. Okay, so we're going to do the partial in parentheses first for these guys. Okay, looks good. So we're going to plug in our r sine of phi, because we found that this is our AR because it is the term before the r hat vector. So this is our magnitude in the r hat direction, labeled as A sub r. Okay, so let's plug that in. Times 1 over sine theta, partial with respect to phi, and then we have r sine of, let me keep these phis the same, sorry, r sine of phi. Okay, and the theta hat plus 1 over r, actually let me distribute the negative, minus 1 over r, times the partial of r sine phi d theta. Okay, so, oh, and this also has a vector direction here. R hat, ooh, I guess it should have been there, but it wasn't. Again, I'll try to be more consistent with my phis. Okay, phi and phi hat direction. Okay, so looking at this, let's start on this side of the expression. So do we have any theta components? No, we actually don't. We only have a phi hat, and those are different, right? Because we have theta and phi in this coordinate system. So phi and theta are not equal. We don't have any theta terms. So this is going to be like the derivative of a constant, right? So like it'd be like d over d theta of like 2, you know, is equal to 0. So this whole piece is going to go to 0. 0. Okay, but this piece here, we do have a phi piece. So we are going to take the derivative of this one, okay? And we're going to have to do what's inside the parentheses. So let's see. So we have a phi piece there, we can pull this r out because we only have a derivative with respect to phi. So let's keep the phi pieces on the inside. Anything else we can treat it as a constant and pull it out. Okay, r 1 over sine of theta respect to phi of, oh sorry, pulling the r out, r multiplied by d over d phi sine of theta. Okay, so what is the derivative of theta? Well, that is, or cosine of, what is the derivative of sine of phi? It is cosine of phi. Sorry, I'm doing this a little bit too late tonight. I think I'm, losing my mind a little bit maybe. Okay, r. Okay, so these guys cancel, right? Because we have 1 over r and r, so they're just going to become 1. So we're going to end up with cosine of phi over sine phi, and I should have brought down that vector direction all time, so make sure that you don't forget that. That's very important. Vector direction is super important. Okay, so we're going to end up with cosine of phi over sine of theta in the phi hat direction. Okay, let's double check and make sure that one is correct. And yep, we are good. Okay, so that's our final solution there. So just to recap, the way that we solve for this is take your original vector, okay, figure out what components you have and which ones you don't, cancel what you can in your expression, plug in your magnitudes, okay, do what's inside of the parentheses first for the partial. You can pull out whatever components you can treat as constants, and then go ahead and solve the derivatives. So same approach for all of the coordinate systems here. Plug in your terms and cancel. All right, so we looked at how to find divergence and how to find curl. And next, we're going to go ahead and go forward into some of these divergence and Stokes theorem problems and plug in our divergence and curl results and then solve for the left-hand side and the right-hand side of Stokes theorem and divergence theorem respectively and prove that they are equal. So let's go ahead and move on to those problems now.